Okay, so in this video I'm going to look at the 2016 Paper 1 AS exam. So let's start off with question 1. So we've got a jet engine going here. So as the aircraft moves forward, air gets sucked into the engine and then it's using an explosion is propelled out the back of the jet engine, which is why the aircraft moves forward, because if we propel air that way, apply a force on air that way, the air will apply a force this way. Okay, so let's get started with the question. So, state what happens to the momentum of the air as it passes through the engine. Well, what you need to do is you need to increase the momentum of the air, because that then in turn increases the momentum of the aircraft. Okay, so fairly straightforward. Explain using appropriate laws of motion why the air exerts a force on the engine in the forward direction. So this is going to be about using Newton's second and third laws. So first thing is, if the air's momentum increases, it must have experienced a force from the engine. And if the air experiences a force from the engine will experience an equal and opposite force pushing it forward. So let's get that down. All right, so that's our answer there. Let's move on. In 1 second, a mass of 210 kilograms of air enters at A. The speed of this mass of air is increased by 570 meters per second as it passes through the engine. Calculate the force that the air exerts on the engine. So we're going to be using Newton's second law. So Newton's second law is that force is the rate of change of momentum. So if we've got a fixed mass, and then what we're going to do is multiply that by the change in velocity, which is 570. And this all happens over a period of 1 second, so we divide the whole thing by 1. So if we get my calculator out, 210 times 570 gives you 119,700, so that's going to be 1.2 times 10 to the 5 newtons there. Okay, so when an aircraft lands, its jet engines exerting a decelerating force on the aircraft by making use of deflector plates. These cause the air leaving the engines to be deflected at an angle to the direction the aircraft is travelling in, as shown. So what we can see is the air is coming in here and being deflected like this. So essentially, the deflector plates are applying a force to the left on the air, which means the air is applying force to the right against the motion on the deflector plates. The speed of the air leaving B is the same as the speed of the deflected air. Explain why the momentum of the air changes. So here, although the speed stays the same, we know the direction of the air has changed, and momentum is a vector quantity, so if its direction changes, that means it has itself changed. Okay, so let's carry on. The total horizontal decelerating force from the deflector plates is 190 kilonewtons. Calculate the deceleration of the aircraft when its mass is 7.0 times 10 to the 4. So effectively what we're going to be using F equals ma. So this would normally calculate the acceleration, but because it's against the motion, effectively in this circumstance it will calculate the deceleration. So instead of putting a negative sign with a force, I'm going to keep it as a positive number, because that's how we're going to end up with deceleration, not acceleration. So we need to divide by the mass, so 7.0 times 10 to the 4. So let's do that. 190,000 divided by 7 times 10 to the 4. And it comes out as 2.71 blah, 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 blah. So it's going to be 2.7 meters per second squared. I'm going to leave that as a positive number because it asks us to calculate the deceleration. If it wanted the acceleration, that would be a negative number. So the aircraft lands on the runway traveling at a speed of 68 meters per second with the deflector plates acting. Calculate the distance the aircraft travels along the runway until it comes to rest, assuming that the force stays the same. So what I'm going to do is write our CVAT. So we want to know the distance. We know the initial velocity is 68. We know the final velocity is 0 because we wanted to bring it to a stop. We know A is going to be minus 2.771 blah blah blah, and we don't know what the time is. So that's our basic SUVAT setup for this equation. So we want an equation without time in it, so we're going to use v squared equals u squared plus 2as, because time is a thing we don't have and we don't want. And we want to get the displacement. We know v is 0, so it's going to be minus u squared over 2a. So this is where it's going to be helpful that the acceleration is negative, because the signs will cancel each other out. So it's going at 68 squared divided by 2 divided by 2.71 blah 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 blah. And that comes out as 8.53. So it comes out as 853 odd. So that's going to be 8.5 times 10 to the 2 meters to two significant figures, which would be appropriate here. Suggest why in practice the decelerating force provided by the deflector plates may not remain constant. So the most likely thing to change is that as the aircraft slows down, a smaller amount of air will go through the engine per second. So we'll get a smaller rate of change of momentum of that air, so it's giving it a smaller force acting on the deflector plates. Alrighty, and that's what we've got written there, an explanation of what I've just said. So that finishes question 1. Let's go on to question 2. Alright, so question 2, we've got a microwave, and we want to use it to investigate some stationary waves, and we're going to try to find the frequency of the microwaves emitted by the transmitter. So suggest how stationary waves are formed. Well, we can see here we've got a source of microwaves over here, and we've got a surface it can be reflected off. So you're going to get waves coming along from right to left, reflected, and then go back across. And where those two waves meet, we're going to get superposition occurring, which is how we can make a stationary wave. So let's get that down. Okay, so that's what we've got there. Just a quick thing to highlight, be very careful here. Loads of people write superimpose, which is just the wrong word. Superimpose doesn't mean anything in terms of waves, so be very careful with your terminology. Okay, so the student removes the turntable and places a bar of chocolate on the floor of the oven, then switches the oven on for about a minute. When the chocolate is removed, the student observes there are 3 small patches of melted chocolate with unmelted chocolate in between them. Now we've got a half-size diagram of the chocolate bar. Suggest why the chocolate only melts in certain positions. Well, it's going to melt in places where the microwaves give the water molecules a lot of energy, and that's going to be at antinodes, where the water molecules in the chocolate are going to be vibrated the largest amount. So these are going to be antinodes with nodes exactly in between them. So that's the explanation there. Okay, and that's what we've got here. So calculate by making suitable measurements on figure 4 the frequency of the microwaves used in the oven. So what we're going to do is we're going to measure the distance between the 2 furthest points, because that's going to represent 1 wavelength. So when you measure that, you find it's a distance of 11.8 centimeters, and that's going to be to 1 wavelength. So we've got the wavelength from measuring it is 11.8 centimeters there. So now what we can do is use the wave equation. So get it like this, and we're going to do the speed. So it's on the EM spectrum, so this is the speed. We we want the wavelength in meters, and when we do that, u times 10 to the 8 divided by 0.118, we get 2.54, and that's going to be times 10 to the 9 hertz, the unit of frequency there. Okay, so that's part 3. Explain why most microwave ovens contain a rotating turntable on which the food is placed. Well, you don't really want your food cooked in some places and raw in others, so it's essentially a way of changing the location of the antinodes in the food so it gets cooked uniformly. Okay, so that finishes question 2. Figure 5 shows the tensile strain graph for 4 materials, A, B, C, and D, up to their breaking stress. Okay. So question, what is meant by tensile stress and tensile strain? So tensile stress is the force acting to extend a material divided by its cross-sectional area. And then tensile strain is the extension divided by the original length of the material. So let's get this down. Okay, so those are your definitions. Be very careful to make sure you include cross-sectional when you describe the area, just having areas not too vague, and make sure you're saying that it's the original length, not just the length there. So, identify a property of material A using evidence from the graph to support your choice. So let's have a look at graph A. So we can see that A just has a straight line section. There's no region of plastic deformation for A. So that tells us it is a brittle material. All right there, so that's a property of A and how we know. So let's go on to part 3. So a cylindrical specimen of the material, so we know it's got a circular cross-sectional area, and it has this diameter, and it has a breaking stress of 1.3 gigapascals. Calculate the force. So force is going to be stress times the cross-sectional area. So that's 1.3 times 10 to the 9, because it's in gigapascals, times by pi, times by 1.5 times 10 to the minus 4. That's the diameter squared. We'll divide that by 4 because we actually need pi r squared there. So let's do that. So 1.5 times 10 to the minus 4 squared times by pi divided by 4 times by 1.3 times 10 to the 9 gives you 22.97 blah blah blah. So that's effectively 23 newtons to 2 significant figures, which is appropriate here. Discuss which of the 4 materials shown on the graph is most suitable for each of the following applications. A cable supporting a lift in a tall building, and a rope or cable attached to a person doing a bungee jump. So in either situation, we're going to want that material to have a high breaking stress because we can't afford the material to break in either of these two. So we need something with a high breaking stress. In a cable supporting a lift, you don't want the cable stretching very much as it lifts the lift. Otherwise, if it just stretches, it's not lifting the lift. So you need it to stay pretty stiff. So you're going to want a very high Young modulus there. When you're doing a bungee jump, you want the material to have a large elastic region of so that essentially when you reach the bottom, it takes a long time to decelerate because you don't want to be decelerated very quickly. So you want it to have a low Young modulus in order to do that. Okay, so let's start getting that down. Let's start off with the lift. Okay, so let's review what I've got here. So I would pick material C to use in a lift. So we need it to be able to survive very high forces, so high stresses, and we also don't want it stretching very much as we apply those forces because we want to actually lift the lift. A and B I don't think would be suitable because they have a very short region of plastic deformation. B is slightly longer than A, but in both cases, if you accidentally overloaded it, which let's face it probably happens quite a lot with a lift, it would immediately fail if you did that, which would be very dangerous. D has a very low breaking stress, so it's not going to be suitable because lifts have large forces involved. So that would be my logic for picking material C for the lift. In terms of the bungee, so then for the bungee cord, I am opting for material D, because what you want to do is minimize the force experienced by the person when they reach the end of the bungee jump. So you need it to extend a large amount for the same force. So we want material D. Because if we stop in a short distance, what that means is the force actually on the person is going to be much larger, because it's still got to do the same amount of work to stop the jumper. So I'm picking D for that one. Okay, so that's finished that part. Let's go on to question 4. A wire probe is used to measure the rate of corrosion in a pipe carrying a corrosive liquid. The probe is made from the same metal as the pipe. So we've got a diagram of the probe. The rate of corrosion of the wire in the probe is the same as in the pipe. So the wire in an unused probe has a resistance of 0.070 ohms and a length of 0.50 meters. Calculate the diameter if we know the resistivity. So you can calculate the resistance of a component if you know its resistivity, length, or area. So it wants the diameter of the wire, so we can see by rearranging that equation, the area, or pi d squared over 4, is going to be equal to the resistivity times length divided by the resistance. So that means the diameter is going to be the square root of 4 rho L over pi r. So let's put the values in there. So we've got 4 times 9.7 times 10 to the minus 8 times 0.5 divided by pi divided by 0.070. Square root of that, and we get a value of 9.392 blah blah blah. So 9.4 times 10 to the minus 4 meters, or I suppose we could go 0.94 millimeters there. Alright, so that's our diameter. So in order to measure the resistance of a used working probe, it's connected in the circuit shown. It's a very complicated way of measuring it, but alright. When R3 is adjusted to a particular value, the current in the cell is 0.66 amps. Calculate the total resistance of the circuit. You may assume that there's no internal resistance. So the total resistance is going to be equal to the EMF divided by the current through the battery. We're essentially applying Ohm's law to this cell. So as far as this cell is concerned, it's just connected to some resistance, which I'm calling RT, and there's a current going through it of I. So that's 1.5 divided by 0.66. So let's calculate that, which is 2.27 blah, 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 so 2.3 ohms. Okay, so let's continue on. So the resistance of R2 is 22 and R3 is 1.1 ohms. Calculate the current in R3. So we know the potential difference across these two this section is 1.5. We know the total resistance, so we can work out the current is potential difference divided by the total resistance in that loop. So it's 1.5 across it plus 22 plus 1.2. So 1.5 divided by 23.2 gives you 0.0647 blah, blah, blah. And so you get 0.064 amps. I sense Kirchhoff's current law coming here. So we want to calculate the resistance of the probe when the resistance of R1 is 2.4. So let's find the current going through the probe. that's going to be the total current minus the current we've calculated in 4.3. So the total current is 0.66, which we found earlier. And we've just got this other current, which was 0.064. So the current going through the other two resistors is 0.66 minus the answer. So that's 0.59 whatever. So the potential difference across the 2.4 ohm resistor is going to be the current times by 2.4. So let's multiply our answer by 2.4, ends up being 1.42. So the potential difference across the probe is going to be 1.5 minus the potential difference across 2.4. So 1.5 minus the answer gives you the potential difference across it, which is 0.0711. So the resistance of it's going to be potential difference divided by the current through it. We just worked out the current through it. It's 0.59 blah 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 blah. And when we do that, we come up with an answer of 0.119 blah blah. So it's going to be 0.12 ohms there. Okay. So that's that one complete. Calculate the percentage change in the diameter of the probe when its resistance increases by 1.6%. So we should know that resistance is equal to K, a constant, divided by A, which is linked to K over D squared. So essentially, if the resistance is increased by 1.6%, each of the diameters must decrease by 0.8%. So let's get that down. So what's going to happen is they're going to decrease diameter by 0.8% because it's squared. So 0.8 times by 2, you can see, gives you 1.6% change. So it's very much like the stuff with combining percentage uncertainties. The same works here. Okay. So a voltmeter is connected between points A and B in the circuit, and R3 stays at 1.2. Explain without calculation why the reading on the voltmeter does not change when the cell in the circuit is replaced with another cell, the same EMF, but significant internal resistance. Okay, so internal resistance is going to mean the potential difference across the resistors is decreased because the terminal voltage is now going to be less than the EMF. Okay, but the potential difference across the two loops, if you like, of the resistor section is still the same because those two are still in parallel with one another. So now what we need to do is look at the potential difference across the first resistor in each case. So that's what I'm going to do. So we know that the terminal voltage is going to be applied across both. So let's the potential difference across R1 is going to be equal to the terminal voltage times R1 over R1 plus the potential difference across the probe. Potential difference across the probe? What utter nonsense. The resistance of the probe. So let's calculate that ratio. So that's going to be 2.4 divided by 2.4 plus our answer from the previous part, which is 0.95 times whatever the terminal voltage is. Potential difference across R2 is going to be still the terminal voltage because that's potential difference. So its resistance was 22 over 22 plus 1.2. So let's do that. So 22 divided by 23.2 gives you 0.948, so 0.94 volts. So around each loop, they're going to have the same potential difference across the whole section, they lose the same amount of potential across the first resistor in the section. So essentially, A and B are at the same potential, therefore they are going to have a potential difference of 0 between the two, as long as our voltmeter is not has infinite resistance, so it doesn't affect our circuit. Alrighty, so if we didn't have the internal resistance, this V in these equations would just turn into the EMF instead of V, but that wouldn't change the relationship between them. The potential difference would still be 0, so the voltmeter should read reading 0 as long as it has infinite resistance. Okay, so that's that one there. Let's move on to question 5. Okay, so we have a photocell which uses the photoelectric effect to provide a current in an external circuit. So essentially, if photons of high enough energy arrive, the electrons can travel to this circuit, and so you get a current flowing. That's how it works. Electromagnetic radiation is incident on the photoemissive surface. Explain why there's a current only if the frequency of the radiation is above a certain value. So the frequency needs to be above a certain value because the photon energy needs to be greater than the work function in order for electrons to be emitted. Alrighty, so that's what we've got there. Fairly straightforward to answer that question. Okay, so state and explain the effect on the current when the intensity of the electromagnetic radiation is increased. So as long as the photon energy, the individual photon energy stays the same, higher intensity means more photons arriving per second, so you're going to get more electrons emitted per second, so a higher current. Alright, so that's the explanation to 5 part 2. So let's move on. So a student investigates the properties of the photocell and uses a source of fixed frequency and observes that there's a current in the external circuit, so the frequency is above the threshold frequency. The student then connects a variable voltage supply, so the positive terminal is connected to the electrode with a photoemissive surface, and the negative terminal connected to the wire electrode. Okay, so essentially what we're going to do is we're going to try and stop there being any photo emission using that. And as the student increases supply voltage, the current decreases and becomes 0. The minimum voltage at which this happens is called the stopping potential. The student's new circuit is as shown. So essentially, photons coming in will release electrons here, creating a current this way. And this power supply is essentially going to do work to try and stop electrons being emitted from the material. And when we find the stopping potential, we know the work done by the power supply is equal to the kinetic energy of the electrons when they're emitted. So what we've got, so we've got the work function of our material, and we've got the frequency of the radiation used. Calculate the max kinetic energy of them. So we're using essentially this equation right here, and this equation calculates the maximum kinetic energy. So we want that in joules, so we're going to do the photon energy, which is 6.63 times 10 to the minus 34. That's Planck's constant. We're going to multiply that by the frequency, so 7.23 times 10 to the 14. And we're going to subtract from that the energy in joules, and we'll get an answer of, let's do that now, 6.63 times 10 to the minus 34, and 7.23 times 10 to the 14. Let's correct that now, 14. Minus 2.1 times 1.6 times 10 to the minus 19. And you get an answer of 1.433, blah, blah, blah. So 1.4 times 10 to the minus 19 joules, to two significant figures, which would be appropriate there. Okay, so use your answer to 5.3 to get stopping potential for the surface. So at the stopping potential, the maximum kinetic energy is equal to the work done by the power source. So essentially, to get this, we're going to do kinetic energy divided by the charge of an electron. So our previous answer divided by 1.6 times 10 to the minus 19. We get 0.895. So that's going to be 0.90 volts there. Okay, so the student increases the frequency of the electromagnetic radiation. Explain the effect this has on the stopping potential. So higher photon energy for the same work function gives higher kinetic energy. So that means it's going to take more work to stop it being emitted. The charge of an electron stays constant, so that must mean a larger stopping potential. All right, so that would be my explanation of that there. So that finishes question 5. Let's move on to question 6. So helium is the second most abundant element in the universe. The most common isotope of helium is 4,2He. The nucleus of this isotope has a rest energy of 3728 megaelectron-volts. In 2011, at the relativistic heavy ion collider, anti-helium nuclei were produced, which would have the same rest energy as this. It suggested that an antineutron can decay. Sorry, hang on, I've skipped a bit there. Nuclei of antihelium are made up of antiprotons and antineutrons. It suggested that an antineutron can decay to form an antiproton in a process similar to beta minus decay. In one particular collision between antihelium nucleus and a helium nucleus, the nuclei are annihilated and 2 photons are formed. So we've just been given a ton of information, so now we need to process that. So state what is meant by an isotope. So isotopes have the same proton number but different numbers of neutrons. So 2 isotopes of the same element have the same proton number and different neutron number. So that's the 2 parts to give you the 2 marks for this question there. Okay, so moving on to part 2. Explain why 2 photons are formed instead of a single photon when a helium nucleus annihilates with the antihelium nucleus. So if we produced just 1 photon, that would violate conservation of momentum. So we need to produce 2 photons traveling in opposite directions to keep momentum conserved. Okay, so let's get that down. All right, so that's that one there. So let's move on to part. Calculate the data using data from the passage, the maximum frequency of the photons produced in this annihilation of the nucleus. So the total energy is going to be the sum of the rest energies of the 2 particles. So 2 times by 3728, giving us a total rest energy available of 2 times 3728, 7456, and it was mega electron volts. So let's convert that into joules. So multiply by 1.6 times 10 to the minus 13, because it's in mega electron volts. You 1.19 blah 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 times 10 to the minus 9 joules there. That's your total energy available. So then that's going to be equal to the total photon energy. So the frequency of 1 photon is going to be the total energy we have available divided by 2, because there's 2 photons, and divide by Planck's constant, minus 34. And when we do that, so divide by 2 divided by 6.63 times 10 to the minus 34, and we end up with 8.999 blah blah blah. So that's going to be 9.00 times 10 to the 23 hertz there, because we're going to give it to 3 significant figures because the Planck's constant value we're using is 3 significant figures. Complete this equation for the possible decay of an antineutron. So we must be producing something positively charged, so our charge is conserved. We are also going to, if it's like beta decay, it's not going to have any contribution to the nucleon number. So what we're looking at is an anti-electron there, and therefore to conserve lepton number we're going to need an electron neutrino, which is going to contribute nothing to either the charge or the nucleon number. So what interaction would be responsible for the decay in 6.4? So in this expression here, we've got a kind of beta decay which is caused by the weak nuclear force there. So that's what's going to be responsible. Okay, so that completes this paper. I hope you found this useful to review this paper. So if you have any questions, please feel free to comment and ask. I'll try and get back to you as soon as I can. If you've noticed many mistakes, again, please do point those out so I can get those fixed. But thank you for taking the time to watch.